Hello students and my friends. We have seen first law of thermodynamics. Mathematically, we write it as dq is equal to du plus dw. So this is differential form. And now we are ready to see what is the second law of thermodynamics. To see what is the second law of thermodynamics, we first need to see what is mean by heat engine and what are their types. So we are going to see some types of heat engine, and there are various types. We are using book of Zimansky. So in that you have gasoline engine, then you have diesel engine, you have steam engine, so on. So I will discuss in detail about the gasoline engine, and then I will tell what are the changes in diesel engine and steam engine. But the basic principle is same. The principle of heat engine is the machine or the mechanism which absorbs or collects heat and converts it into the work done. So we will see what is the heat engine. Suppose there is one system and there is some heat supply, let's say Qn, and using this heat some amount of work is done and remaining heat is thrown out or rejected. So we will write Q in, Q out, or you can say Q1 and Q2, but the basic principle is same. Q in is a heat supplied to the system and work done is W. So from energy conservation you can immediately tell W is equal to Q in minus Q out, or you can say Q in is nothing but W plus Q out. So this is the work done during the process of one cycle of the heat engine. So what we will see what is the cycle of heat engine. So schematically we can write in this format. We can write this, or we can draw this diagram, or there we can draw one another diagram like this. So this is a system. So we provide heat, and here it converts into work done, and remaining is returned to the surrounding. Or we will have different type of reservoirs. So from which we are absorbing heat is called as a hot reservoir, or we will denote it by H, which has higher temperature, let's say T1, and Q out is supplied to C, or it is thrown back to cold reservoir, so it is named as T2, or we can name it as TH, that is temperature of hot reservoir and temperature of cold reservoir. So whatever we can use, and depending upon it our formula will look differently. So this is basic schematic. So there are names for these reservoirs. So I will quickly write those names. This hot reservoir or high temperature reservoir is also called as source because it supplies heat, while the cold reservoir is also called as sink or low temperature reservoir. Okay, so any of this you can use as a terminology. So we will basically use Q in, Q out, and TH and TC. So for conceptual understanding we will use this subscript. H is for hot, C is for cold. We will draw PV diagram for gasoline engine. The first line is first process is done in this way. So this is isobaric process, so pressure is not changing. This process is called intake stroke. After this stroke, the diagram will move ahead like this. So this second curve is an adiabatic process. No heat is exchanged, or no heat is exchanged in this process during this process. Then for the third process, that process is isochoric, so volume is not changing. Then again we get back the same type of curve, and this process is again adiabatic, So let me call this number 4 and this is number 3. Similar to number 3, there is process 5 which is also isochoric, and then again back to 6 process. So first process in this direction and 6 process is backwards. I will tell what are these processes and what they are named as or what they do. So first process is intake process. In this process, the chamber of gasoline is filled with the air. So the air from the surrounding or the atmosphere is entered in the chamber of combustion, because the shaft is going to release. So if you see the shaft, suppose this is shaft and this is the engine, so there is a small gap to enter the air from sides, and this goes in upward direction. So there is gap and this gap is filled with the air. So external air comes in and the gap is filled for the first process. So in this process, pressure is maintained at the atmospheric pressure. Now in the second process, the shaft starts to compress back. So the second process is called as compression stroke. So in the second process, you can see here the volume is going to decrease but pressure is going to increase. Okay, so in this process the shaft is moving in this direction. The connection of external so during this process, the connection with the external air is not maintained. So external air cannot enter inside during this process, or after any only for first and second process the air can enter in or out. Okay, so the in the second process the compression takes place, so it is called as compression stroke. Then third process is very shortly happen, and that is the spark. So spark takes place at a constant volume because it is very short process, and the shaft or the piston is at the minimum level. Okay, so at this process the spark takes place, and due to the spark the shaft or the piston is thrown away, and this is called power stroke, and this is represented by the number 4. So in this process pressure is going to drop and volume is going to increase because the shaft is again moving back, or it is creating some space between the chamber. And in fifth process is called exhaust. So it does that, it reaches the same point where we started. At this point internal air can go outside, which is burned and which is hot. So hot gas will be ejected out at this point, and 6 number process is called exhaust stroke. So remember 5 number process is exhaust and 6 number process is exhaust stroke. So there are different strokes, and we can see that how this process is going on. So what we will do for this process, we will assume that process number 2 and process number 4 are adiabatic processes. So these are adiabatic processes, and the curves 3 and 5, in this process the heat is entered. So I will write here Qn, and here the Q will gone away or outside. So Q in and Q out. But at second and fourth process there is no exchange of heat. Suppose we assume that the temperature here is T1, here it is T2, it is T3 here, then here it is T4, and again back to T1. So T1 is related to atmospheric pressure and temperature. Now while calculating work done, this part is not going to take part, because when you are considering first process and sixth process, they are equal and opposite to each other. So the area under the curve is same, but the direction is opposite. So dw minus dw, that will become 0. So we are only interested in the next curve, process 2, 3, 4 and 5. So this will consist of the engine cycle. So in this cycle we can consider these two curves where the heat is exchanged. Qn is equal to, so that is integration of dq during the third cycle. So we can write it as cv integration of dt. So we can check where dt is changing. Dt is changing from t2 to t3 during this process. So I will write it as, this is from T2 to T3. So T3 is obviously higher temperature. So this will become Cv into T3 minus T2. Similarly, we can calculate Q out and it turns out to be Cv T4 minus T1. So here both quantities Q in and Q out are taken to be positive. In the second law we generally deal with, or in heat engines we generally deal with the magnitudes of heat and work. We have seen the efficiency is given by 1 minus Q out divided by Q in. So if we put the last derivations, this derivation Cv will get cancelled out. So we will get 1 minus T3 minus T2 divided by T4 minus T1. And it will turn out, you will do this as your homework. So you will get that T3 minus T2 divided by T4 minus T1, this turns out to be T1 upon T2. So T1 is here lower temperature. While discussing the heat flow in heat engine basic terms, we have considered T1 to be higher temperature, but here look, T1 is the lower temperature. So in heat engines we generally deal with TH and TC, because we will not get confused with T1 is higher or lower. But here we will consider, because there are 4 temperatures, so we will consider 1 and 2 and 3 and 4. So this ratio is equal to T1 upon T2 and this is equal to T4 upon T3. Okay, so the highest temperature here is T4 and then T3. So this ratio is exactly equal to T1 upon T2. So using this we can write eta is equal to T1 minus T2. So we will reconsider this while discussing the second law of thermodynamics. So now there is another engine which is called diesel engine. So in this process all the process is same. In the third process is isobaric instead of isochoric. So this will be curved like this and then again back to this and again this. So this will be okay, first, second, third, fourth, here it is fifth and sixth process. So it also has 6 processes, and again we can ignore this part. So we will consider only this part. The heat will be entered from this and gone away from this. So this is Q in and this is Q out. Now there is another engine called steam engine. It will also have some different PV diagrams. So there are number of various engines we can study. So the basic gasoline engine we discussed was, is used in our motorbikes. So it is a very daily example we can see. And so the thermodynamics of that engine is as we discussed now. Now we will reconsider this efficiency eta. Eta is equal to 1 minus T1 upon T2. Now we will consider that the efficiency of the engine is 100%. So at what temperature will you get this this efficiency? Because this efficiency is not depending on the material or the system of the engine. So what you are using gasoline, you are using it in air or in the nitrogen atmosphere or in the oxygen atmosphere. You are carrying out these processes inside the wood or inside the iron. So that is not dependent. Obviously the processes, two processes are adiabatic, so you have to be insulated surroundings, but still there is no dependence on all that factors here. So if eta is equal to 1, this turns out to be T1 upon T2 is equal to 0. So this can happen in 2 different cases. If T1 is equal to 0, then also I will get this ratio. So what does this mean? T1 is lower temperature here and T2 is higher temperature in the cycle we have discussed already. Now T1 if T1 is 0, so what is T1? So it is the temperature which is lower temperature. It is same as the room temperature. So room temperature we cannot take 0. So 0 is not 0 Celsius, it is 0 Kelvin, right? So we cannot reach up to that temperature, or this is exactly equal to minus 273 degrees Celsius. So we cannot reach at that temperature if we are traveling on bike. So this is not possible. So T must be some positive number and T2 will be higher than that. So this ratio must be 1 minus T1 by T2. This must be less than 1. So there is one another quantity which many of us will not discuss. So that quantity is, or that case is, T2 is infinite. So that is also not possible, because to get infinite temperature we have to provide large number of heat, and that is not possible, or that is not efficient way to drive a car or drive a bike. So in any case we are not getting the efficiency is equal to 1. Or if we consider another formula, eta is equal to 1 minus q out upon qn. So from this formula also we can think that efficiency cannot be equal to 1, because q out is always less than qn, and we are considering here only magnitude. So this is only positive quantity. So this is positive quantity and less than 1. So 1 minus something less than 1 is always less than 1. So efficiency of any heat engine is always less than 1, and this is nothing but the second law of thermodynamics. So it is very important concept in the thermodynamics, or we can say it is at the core of thermodynamics. Okay, here we are looking at the Kelvin statement. He says that it is impossible by means of inanimate material agency to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects. So what he want to suggest is, inanimate material agency means here engine, and to derive mechanical effect is work done here. Okay, so what he want to say, it is impossible to make such engine which can derive work done from any portion, that means that the cycle, and by cooling it below the temperature of coldest. So we cannot go further of the coldest of the surrounding temperature. So if room temperature is T, so our T1 cannot go beyond that. I mean it cannot be colder than that. So there is certain limit on efficiency. So even as I discussed, there is some limit. We cannot go to 0 degree Kelvin. Still we cannot even go to 100 Kelvin or to 200 Kelvin. So our room temperature is considered to be 300 Kelvin, or in winters it may drop to 270 or 280 Kelvin in certain cold regions. But so there is limit, so it will not reach up to 0. Suppose the temperature is 295 Kelvin. Okay, so and suppose the heat is generated and temperature is increased by 200 Kelvin. So even then the T2 will be this. So if you calculate T1 upon T2 and calculate efficiency from that, and suppose the temperature is now 280 Kelvin, and even this process the temperature is increased by 200 Kelvin, then also you can calculate efficiency, what is the efficiency in this case, and you will note the difference, that at lower temperature we will get the higher efficiency. So there is certain limit by surrounding itself, so that is meant by Kelvin statement. Then there is another statement by Planck. Planck says that it is impossible to construct an engine which working in complete cycle will produce no effect other than raising of the weight, here it means the work done, and cooling of the heat reservoir. So this means heat is not rejected. Okay, or cooling of heat reservoir takes place when the internal energy is used to do the work. Okay, so what does this mean? We cannot construct such engine so that it will only work and cool the system. So the byproduct is the heating. So if you drive your bike or car, you can observe that the car engine or your bike engine gets heated after some time. Okay, because you cannot cool it. So this statement states that. Now there is another statement, Kelvin Planck. So that is the combination of Kelvin and Planck, because there are some correction in that, or there are some new words we see that Kelvin has not used the word engine, so we will replace it. So we will be it will be easier to remember. So this statement says it is impossible to construct an engine that operating in a cycle will produce no effect other than extraction of heat, that is Qn. So it will absorb the heat from the reservoir, which will be hot obviously, and the performance of the equivalent amount of work. So this means Qin is equal to work done. So it will not reject any heat, or it will not release any heat to the surrounding, or to the cold reservoir. So as we have seen these three statements, mostly we use Kelvin Planck statement as a definition of second law of thermodynamics, but there are some easier and mathematical terms or definitions we can still use as a alternative of second law of thermodynamics. So first one, as I have already told, efficiency will be always less than 1. Then in other words, it can also be written as Qn is always greater than work done, or Q out cannot be equal to 0, or we can also write Qn cannot be equal to Q out. There is one another statement in which you can state that you cannot have only one reservoir and work done. So at least you have two reservoirs, that is one is hot and one is cold. So we will see both the statements. So this is system, and the heat here is hot and here is cold. Suppose there is no cold reservoir, only heat is coming in the system and it is not going out. So it is not possible according to the second law of thermodynamics. And there is another system which only releases heat. So there is Q out, but there is no Q in. It will not absorb heat from surroundings. So there is only cold reservoir, there is no hot reservoir, and the system itself will use its internal energy and do the work, and it will release some heat. So that is also not possible. System itself will not do any work. So that is the alternative statement for second law of thermodynamics, or you can say that is consequences. That are all are consequences of second law of thermodynamics. So you should have both hot and cold reservoir. Only one reservoir is not possible. So that can be your alternative statement. Now in the next lecture we will see what is refrigerator and what is closure statement for second law of thermodynamics using the concept of refrigerator. Thank you so much.